Yeah, we're gonna
I have a question
switch.
actually on the conversion quiz.
Yeah, so
I couldn't get.
I was going ahead and doing a couple quick lab concept questions while I was trying to figure out the software for streaming, and now that that's working, though, don't watch that video too closely though, because that one is going to be delayed by like 30 seconds. So let's go ahead, let's move on to any other questions we might have, whether we want to talk about homework or the online unit conversion quiz or anything like that. Do you have just one or two about the unit conversion quiz?
Yeah.
Let's go ahead and get that real quick.
So the problems that we're using the picometers, for some reason I could not get them to come out correctly. Even though they were, it's 10 to the negative 12, right?
Yes.
Yeah, I was using that, and for some reason all the other problems I could get to come out to the right answer, but those ones kept.
So let's check two things. What's the actual wording of the problem?
So for question number 4, it's a gold atom has a radius of roughly 136 picometers. Calculate the diameter of the gold atom in centimeters.
So we can, if we just forget the unit, and I do this thing that's kind of weird, let's just forget picometers, centimeters for a minute and make sure we're getting the same number without worrying about the number of zeros.
Yeah.
This is...
It was radius to diameter, so you'd have to double the number.
That's the radius, and we want diameter?
Yeah.
It wasn't volume. Well, that seems like it should be pretty straightforward.
Yeah.
So to go radius to diameter, all you do is double
it.
136. So 136 doubled is going to be 272. And you got that?
Yeah.
272 picometers.
Yeah.
That would be 272 picometers times 1 meter is 1 times 10 to the 12 picometers. And then we want it in centimeters, so I do 1 times 10 to the 2 centimeters per 1 meter.
Yeah.
Right? That will cancel out my picometers, that will cancel out my meters. I'll get something that's 10 to the minus 10. So I should get something that's like 272 times 10 to the minus 10.
Yeah, that's what I was getting.
However, I think it's going to want you to put this as 2.72 times 10 to the minus 8 centimeters.
Okay, that's...
And it might be looking... Now, this is one of those things where these softwares can kind of be frustrating at times, right? Because these two numbers are mathematically equivalent. But if the computer's looking for a particular format of the number, it could throw it off.
Cool.
I thought there was something with like the volume of the atom rather than just the radius, but I might be thinking of a different problem.
There were 2 other problems that included picometers. One of them had volume on it.
Yeah, so it could be just a unit version like that. I think the quiz does specifically ask for proper scientific notation,
Okay. Cool.
but I would accept either answer on a quiz or an exam. Yeah.
So when doing unit conversions like this, do we assume the dimensional analysis doesn't change the amount of sig figs in the problem?
Yes. So these units, when we say 1 meter has 1 times 10 to the 12 picometers, that's by definition.
Yeah.
Anything that's by definition is infinitely precise.
Okay. Okay.
Right? Now that's different. That is very different than 2.54 centimeters per an inch. That's not definition. That's a conversion. And if you go online, you can look up a certain number of sig figs associated with that.
Yeah.
So there are places where it's like, no, this one the sig figs matter, but these that are definitions are infinitely precise.
And so how do we distinguish what's a definition and what is...
So these, like the pico, centi, milli, the prefixes are all definitions, right? And then the other one I mentioned that's handy to know is centimeter cubed is a milliliter by definition. So that's also infinitely precise. Yeah.
For the reading, I guess just like your assessments in general, are you going to be pretty intense, not intense, but like on point about the significant figures? And if we have them correct?
So yes, because I'm on video, but also the main thing I'm going to be looking for is absurdity. So if you were doing this problem, you punched it into your calculator and for some reason you decided to round to 1 sig fig, clearly that would be absurd.
Mhm.
Or if you included 10 sig figs, that would also clearly be absurd. I'd like to see that you're in the right vicinity of the correct number of sig figs, and there are problems where I specifically say you need the right number of sig figs to get this one right. But generally, you should be in the right ballpark. Otherwise, I might take a point off, something like that.
And I'm assuming with the equation sheet you've given us, when converting from metric to imperial, those are not definitions.
Those are not definitions, right?
those
So
sig
those,
figs.
and
Okay.
you'll use the number of sig figs that are on the page. I think the
Okay.
page gives you 5 sig figs for those, which is usually going to be more precise than your other numbers.
Okay, cool. Yeah.
But I'm also going to avoid the imperial system as much as
Yeah.
possible. So.
Okay, cool.
Yeah. Any other questions about that? Did it work? Did you try it yet?
I tried to, but apparently Capolly says my account's locked right now. So
That's been happening to a lot of people. The person
yeah,
who was in
this is the third
earlier.
time it's done it this quarter to me.
Government shutdown? No, I don't know. There's another student who had that problem, and I almost had that problem earlier today. There's just, I think, some problem with material, with like back end updates and things like that. Should we move on to homework questions then? Cool. Let me get a quick list. What homework questions would you all like to see? If you know a couple.
21 and 22.
21, 22. Same ones for you? 22?
Maybe just some other ones that I've looked and they're like, oh, maybe
Yeah,
I
yeah.
got it wrong. Those are
19.
the two big ones.
19. Is 22 the last problem?
Yeah.
Yeah.
Cool. I'm curious to see. I made that one like last week. That's a new problem. So
Yeah. It's
we'll
very,
see how it
very,
goes.
very different from all the other questions.
Yeah. I was taking my student evaluations last quarter seriously, and they said the homework didn't represent what was on the exams as much. So I was like, I'm trying to add more problems that are more like a little bit more complex, a little bit deeper, because that's what I do on the exams as well. So let's start with number 19, though.
I have another quick question.
Yeah.
Just in general, could we possibly get like just an answer key for the homeworks? Like they don't have to necessarily have to say every step by step, but just
So that we can know if we did it right.
yeah.
So here's the problem with that. I am very reluctant to give answer keys, which drives my students crazy. I get negative feedback about that pretty regularly. They're like, "We need answer keys," and I'm like, it's a kind of like a teaching philosophy choice I make, with the idea of seeing if you got the answer right or not is not necessarily where the lesson is. Right? It's the building the confidence, having the conversation with the instructor, the LAs, other students, other like people who have other instructors of office hours, getting to that point where you're like, did I do this right? And you can look at your work and say yes, and getting them to say, well, can you explain what your logic here was? And that's really where the learning is. Just seeing the answers, like this attitude of like, I just want to see if I got it right or not, is really.
Well, I don't know if that's
Yeah.
what we're saying. I think
Yeah,
more
it's
like
like-
if we like do this practice, like I would still come to your office hours regularly, even if
And
we had them.
I
it's
should
more
say,
just, like,
let me
check.
take this in other ways. My problem is giving the answers without being able to see the process. So what I'm working on, and I haven't gotten there yet, the lab POW, which we're going to be using in lab tomorrow, is actually capable of having homework assignments on it. So I am hoping to convert some of my homework problems into a lab POW module. So you could like go on lab POW, do homework 1, and it would give you immediate feedback. It would say, yes, you're right. Or it would say, no, you didn't do this calculation correctly. And if I want to get really creative, I'll be able to find the 3 to 5 most common mistakes that students make. And so it'll be like, no, you're wrong. Have you thought about checking this? Right? I can check if the like first digits are correct, and I can say, oh, it looks like you have the right number, but you missed a conversion someplace. Check your units. But that's a project that's not going to be done by the end of this quarter. So I honestly don't have answer keys for the homeworks because I just like having the conversations and kind of like doing that. And the videos are kind of a step I'm pointing at the camera. The videos are kind of one of those like in between digital steps where I am working at creating more accessibility in the content, more ways where you can check your work. I'm perfectly happy to go through as many problems as we can during office hours, but it seems like these are the ones that you're worried about, and the others you're probably doing fine with.
Yeah.
So
Yeah, just for the future, you know, when they
Yeah.
get more complicated.
yeah, totally. But I don't have answer keys.
Right.
So let's start with number 19. What is question 19? Someone willing to read it out? I don't
It
know if
is
it's a short
if
one
the
or not.
stock solution in all of the previous problems is a red dye. Well, I guess we'll have to look at the previous problems. But,
Some, yeah.
but if the stock solution in all the previous problems is a red dye that absorbs light, how would the peak height qualitatively compare between all 4 cases?
Oh, stock is red. Now this really doesn't matter.
When it's saying the peak height, it means in terms of wavelength. That's what I was kind of.
Ooh,
Yeah.
right. So what do we mean by peak height?
Was that like the brightness, or was that the? I wasn't. Yeah.
So I already changed the thing I have on the board. So let's I'm going to cover it, and we're going to think about it a little bit. When you measured your peaks last week, what did you measure about them?
Wavelength and absorptivity.
Yeah, well, absorbance.
Oh, yeah.
Right. So which one was on the x-axis? Which one was on the y-axis?
Absorbed on the one.
Absorbance
So
on
what would we refer to as the height?
the absorbance.
absorbance.
Right.
Okay.
So all this question is asking is, how does absorbance change with the previous problems? Now, if I remember correctly, well, without even looking at the previous problems, I can kind of do some problem solving, right? I can look at this and I can say, okay, it's about absorbance. That means I'm probably going to be using, well, whose law? Beer's law, right? I'm probably going to be using A equals epsilon L. All right, we'll go with the lab version. Epsilon BC. Right? Now, if the stock solution is the same in all cases, is epsilon going to change? Nope. Is the path length going to change? Nope. So I can look at this and say the absorbance is going to be directly related to concentration. And that's all that we have to do is we can say, well, the cases that are more concentrated are going to have a higher peak height, a higher absorbance, and the situations that are lower concentration are going to have a smaller peak height, a smaller absorbance. So we can essentially, without even looking at the previous problems, through reading the question and pulling apart the details, being clued into the fact that we're doing Beer's law because it's talking about food dye and absorbance, we can pull it apart. Now, if you look at the previous problems, they're all dilution problems that have you taking some stock solution, making a bunch of different dilutions. We could take this a step further after we get to that, and we could say, okay, so if we have the absorbance, if we have the concentrations of the previous problems, we could say what the order of peak height, where the most concentrated would have the highest peak height, and then you go down from there. But I don't think it asks you to do it quantitatively, right?
No,
It just
it's
says
qualitative.
So we don't even need to do that, but we could. Yeah. But it seemed like it was the idea of what it meant by peak height was the catch. So yeah, just thinking about the spectrums, we collected the information that's there. Are we ready to move on? That was problem 19.
Yeah, that was one of my questions.
Great.
So that works great.
And then we've got 21 coming up next. Question 21.
In terms of wavelength, but no, it's just a higher concentration.
Which question is 21?
A yellow solution is spectroscopically investigated starting with a stock solution of 35 micrometers.
Was it micro or milli? Oh, micro. Yeah, sorry. Micro. Micromolar, right?
Mhm. Oh, and then there's A through D.
Okay.
Did you want all of them or just?
Which ones are we most interested in? A through D.
Honestly, all of them.
Let's do all of them.
Let's do
What's
all of
what's A asking?
A, the stock solution has an absorbance of 0.742.
Oh wait, I wrote the wrong thing. Absorbance.
Absorbance.
0.742.
And a wavelength of 430 nanometers. What is the molar absorptivity at this wavelength?
So we've got a particular wavelength. We know that molar absorptivity depends on two things. Depends on our wavelength of observation, depends on our material. This entire problem is going to be dealing with yellow stock solution, I think, at the lambda max. Whose equation do we use? Beer's law. Same thing, right? We've got our concentration, we've got our absorbance, and we're being asked to find epsilon. So we look at this, we say 0.742 is equal to epsilon times 1 times 35 times 10 to the minus 6. This is now in molarity. This is in centimeters. This has no units. We've got one unknown variable. Easy to solve, right? Now again, notice it's easy if I set up the equation. If I just set up 0.742 equals x times whoops, that's not enough zeros. 1, 2, 3, 4, 5, 6. That's super easy to solve. But we want to make sure we're understanding the physical world that this is describing at the same time. Right? I also really don't like this. I like scientific notation. But x's get confused sometimes. So when we look at it in terms of the mathematical equation, it's easy, but the question becomes, how do we get to this? How do we get to this idea? Again, it's recognizing the fact that if we've got a absorption, if we've got a lambda max, and we've got a concentration, we're probably using Beer's law and then just plugging in the parts. We also know the general range of epsilons, molar absorptivities for dyes should be
Between
10,000 to 100,000-ish, right? Yellows are typically lighter colors, so since this is yellow dye, I bet it's going to be a little bit lower. But we can solve that now, right? We can do 0.742 divided by 35 times 10 to the minus 6 is going to be, I can't do that in my head. Does anyone have a calculator handy?
why don't you use lambda in the equation?
Oh, right. So remember, lambda doesn't appear in the equation. However, our epsilon depends on lambda. And I think that's going to be part B or part C.
Okay.
So our epsilon depends on lambda. So that's part of why we always use the same lambda for our observation.
21,200.
So that's 21,200.
Yeah.
I almost could do that in my head. Almost. Because I knew that it was 7 divided by 35, like 7 and 35, like 70 would be like half, or like would be double. So, but couldn't get it. That's epsilon. In order to be correct, we also need the units, inverse centimeters, molarity. So that's part A. What's part B ask us?
It says the stock solution is diluted by a factor of 10. What is the absorption at the max wavelength? Do you need to know molar absorptivity to calculate this? Why or why not?
So we got a couple of things we can think about. First off, you notice we're using the same lambda again. So we're going to use the same epsilon again. So we could explicitly calculate this, but let's think about it logically. If you decrease the concentration by a factor of 10, how much should the absorbance go down?
10.
Factor of 10. You don't actually need epsilon to do this. You can just say the absorbance is going to be equal to 0.0742. We can logic through that without actually having to do the calculation, but understanding the Beer's law relationship. If epsilon and B are staying the same, concentration and absorption are directly proportional to each other. Decrease by a factor of 10 of the concentration, the absorption also decreases by a factor of 10. If we wanted to, we could also explicitly do this by plugging in 3.5 times 10 to the minus 6 and repeating the calculation, and we would get 0.0742. plugging in epsilon and the 3.5 times 10 to the minus 6, calculating that. We don't technically need to, and that's kind of the nice like thought process at the end of part B's. Do you need epsilon? No. Can you use epsilon? Yeah. What's part C ask us?
An unknown sample of the same dye has a measured absorbance at the max wavelength of 0.532. What is the concentration of the sample? Same, do you need molar absorptivity to calculate this?
So notice in this case, lambda is still the same. As long as lambda is the same, we don't have to worry about it because epsilon is the same. And we had an absorbance of
0.532.
0.532. 0.532. In this case, do we need epsilon?
No.
Why not?
This is the same stock solution.
Yeah.
Oh, we're in the same wavelength.
Same stock solution, same wavelength, so epsilon is the same, but do we need epsilon to calculate the concentration?
Yeah.
Yeah, we do need epsilon to calculate the concentration. Or at least, that's what I intend the answer to be, right? So if we're using the same stuff, we can say 0.532, whoa, that's a weird looking 3, 0.532 is equal to 21,200 times 1 times concentration. Solve for concentration.
Oh.
Right? Now, technically, and this is what I intended the answer to be, do you technically need epsilon to solve this problem?
Yeah,
Yes.
you need
Technically, no. Because you can essentially take two versions of Beer's law, right? Absorption 1 is equal to epsilon B concentration 1. Absorption 2 is equal to epsilon B concentration 2. Take the ratio, you get absorption 1 over absorption 2 is equal to concentration 1 over concentration 2. Which is really why we define epsilon, right? Epsilon is this thing that gives us a relationship between absorption and concentration. So then you could use this and say, I know the absorptions, I know one of the concentrations, I've only got one thing to solve for. Right? But that is essentially the same thing we're doing by defining epsilon. So, and that is kind of how you define epsilon. Epsilon is always experimentally determined. There's not really a straightforward calculation. There are some calculations, they're very difficult, but typically epsilon is just experimentally measured. The same way we're going to do it in class tomorrow.
Question 4 is an unknown sample of a different yellow dye has a measured absorbance at the same wavelength of 0.334. What is the constant? It's like the same question.
But it's a different yellow dye.
Yeah, no, that's obviously that's
What does that change?
the epsilon.
Yeah. Technically, we can't do the problem anymore.
Yeah.
Right? Does it ask you if you can do the problem?
All it asks is, do you need the molar absorptivity to calculate this? So, I mean, it's kind of asking if you can do it. But.
Right? And again, the reason that we were able to do this was because the epsilons were the same. In this case, in part D, we're going to have absorbance 1 is equal to epsilon, I'll call it yellow 1, BC1, and then absorbance 2 is going to be equal to epsilon yellow 2, BC2. The epsilons won't cancel out anymore. Right? So when I take my ratio, the epsilon's still going to be there. And you could make approximations and arguments here, right? You can say, well, they're both yellow, they probably absorb similarly. Not necessarily true. We don't even know if this yellow has the same lambda max. Remember, there's different ways that things can appear yellow. So in part D, we actually can't do the problem because we've changed the material.
Would we ever have, like, on an actual test, an answer that says we can't do it?
That is an entirely feasible thing where you go, oh, but notice, the fact that you can't do it wouldn't be the important part in the test. It would be, can you do it or not? Why?
Will it be like that format, like how you did it right now? Or will it be like you just give us a problem?
Oh, I would ask you to explain. I would say, can you solve with the information given or not?
Okay.
Explain why. I wouldn't just be like, do this problem.
Yeah.
I would tell you, I would give you some prompt. And again, the whole point of exam questions, quiz questions, homework questions is to see what's inside your brain, not to trick you, despite what some of your other instructors might do. So I would prompt you. I'd say, can you even do this problem? Why not? And then like I might do a follow-up of like, what answer would you get? Or I might even do another follow-up of what information do you need to assume in order to do this problem? Or I would say it even more explicitly. I'd say, assume you had this piece of information. Now can you do the problem? What answer do you get? Right? And I want to see that kind of, because on my exams I do have straight numerical things where I'm just like calculate the answer. And then I also have those concept questions where I'm like, explain to me how you're thinking about this problem and why this would or wouldn't work. So yeah, but I would let you know that I'm looking for that thinking process.
Awesome.
And not try to trick you. Is that it for problem 21?
Yeah.
Great. Let's go ahead and look at problem 22, and I'm really curious to see how problem 22 goes.
I hadn't. You guys have heard it. I have no idea.
That is the new question.
Okay.
So, and I tried to make it relate to the lab we were doing a little bit, and to bring in like much more complicated concepts and ideas of ways we can extrapolate the idea of Beer's law. So, I can't remember what I made the question. So, can you remind me? Like,
Just go on like the paper.
Yeah, it would be much easier.
Yeah. Let's take a look at the paper. So, question 22. Oh, nickel plating solution is made from a combination of materials. We got nickel sulfate, hexahydrate, nickel chloride, hexahydrate, and boric acid in 1 liter of water. The characteristic green color of the solution is caused by the nickel 2+ ions in solution. So, turns out, you know how we had a green solution that was made because it was like absorbing blue and yellow? Like the green dyes we had in lab were made because they were absorbing orange and purple, right? That combination, we mixed blue dye and yellow dye, and that made green. The nickel plating solution is just green, right? And there's a lot of extra information. Actually, this one doesn't even have a lot of extra information. So, using your knowledge of absorption spectroscopy, give 2 ways the solution may appear green. How would the spectra of your 2 possibilities look different? And I kind of already spoiled that one. So, our 2 possibilities are the same way that our green dye in the lab looked green. Absorption peak there, absorption peak there. This is orange. This is purple. This is going to appear yellow plus blue. That is one way we could get something to look green. It's exactly what we did in the lab, right? What's the second way something might appear green?
Chemical reaction or not?
Chemical reaction could be part of it, but this is a stable solution that sits there. It's in that jar. It's how I burned my finger. Still, it's not totally healed. But yeah, it sits there. It's not reacting anymore. It's stable. It's at equilibrium, we would say. Just not even thinking about the chemical solution, just what's another way that we could get green?
Can it reflect blue and yellow? Is that different to that or not?
That would be very similar to this.
If it was absorbing the complement of
Yes, if it was absorbing the complement of green, it would appear green. So what's the complement of green?
Red.
Yeah. So if we had something that was absorbing over here in red, absorbing in red would also there are some other ways that we could get things that appear green, but these are the 2 ways that I was looking for. These are the 2 ways that I was looking for. It's absorbing purple and orange like we had in lab, or if it's just absorbing red. And clearly, if we ran the spectra of different green materials, there would be a really obvious difference in terms of it having two components and absorbing two different colors, or one component and absorbing one color. So we can tell the difference between the two by looking at that. And that's part A. Part B, I don't know if you can do part B yet. How comfortable are you all with molar masses?
No.
Have we gone over that?
No, we're
Okay.
doing that tomorrow.
I was gonna say, I feel like we
Yeah,
haven't learned that yet.
I should have. Well, we have learned molar masses,
Oh, okay.
Yes,
right? That
it's
was
the
a unit, right? That
No,
was.
but like,
I bet we could figure it out. The part that made me pause is I really feel like I should give you the molar masses of the materials rather than asking you to figure them out on this, because we haven't done that yet. It is pretty straightforward. For example, if you looked at the molar mass of boric acid, if you're looking at H3BO3, you'd look up the molar mass of 3 hydrogens, which is 3. You'd look up the molar mass of borate, which I need a periodic table to look up.
Equation sheet has it.
I have the.
Yeah. Sorry,
Yeah, so-
boron is 10.8, and then plus 3 oxygens, which is 3 times 16. That would give me the molar mass. We haven't learned how to do that yet. But if I just gave you the fact that the molar mass was, let me see if I can do this in my head. 48. Let's call it 11 plus 3. If I just gave you that this had 61 grams per mole, does that become more solvable?
Because they give you the grams to-
Right, so there was a step that I was missing in my haste. I think I was planning on this question being done a little bit later, but if I give you the molar masses of each of these, let's go ahead and try this real quick. I'll see how you all do with it, and then I will update the homework assignment. I don't think it's fair. Well, I'm not going to say it. I don't think it's. Well, I'll say it. I don't think it's fair that this one would be on the quiz, so it's probably not going to be on this quiz. Could be on the next quiz. So let's see what I need to do. First off, how else could you get the molar mass of boric acid? Google it. Right? You just type in molar mass of boric acid, and you should get boric acid, HBO. Why did I put H3BO3? Oh, that's what it is. H3BO3. Huh. What did we say? I just erased it. 61 grams per mole. Then we'd also need the molar mass of nickel sulfate, NiSO4 6H2O. Let me grab a calculator. Maybe I can do this. I don't know the molar mass of nickel either, though, so I have to get a periodic table as well.
I have one.
Or you can just Google it. Right? You can just Google molar mass of nickel sulfate, and it'll give you the answer. This is one of probably the most important things to realize in the difference between college and high school. High school, you could probably Google every answer you needed to get. That stops being true. I don't like to ask questions that you can Google the answers to. Those are boring. They're just like, they're facts, they're information. But if you tried to Google this problem, if you Googled why is nickel plating solution green, you would get very complicated answers. You'd get entire pages that you'd have to read. However, if we wanted to get just the molar mass of nickel sulfate, that's 18 times 6.
This will be posted on YouTube, right?
Yeah,
Okay.
yeah, as soon
Oh,
as
it will be?
the video's done. Yeah,
Thank you.
yeah, no worries. Yeah. 18 plus 6 plus the molar mass of nickel. Why can't I find nickel? There it is. 50, we're going to call it approximately 59, plus sulfate, which is going to be plus 32, plus 16 times 4, plus the 6 waters that are also attached for the hexahydrate. So this would be 263. 263 grams per mole. And then we also need the nickel chloride, NiCl2, 6H2O. So that's going to be 59 plus 35 times 2 plus 18 times 6, 237. 237 grams per mole. If we have this information for part B, does the problem become much more doable?
Yeah.
I hope so. I hope so. So, and that's where I gave the hint of like use the molar masses, but again, we didn't get to how we determine molar masses from chemical formulas yet. We're doing that tomorrow. So that's why this question would not be fair for the quiz. I bet industrious students could figure it out if they put the time in.
Wait, I have a question.
Mm-hmm.
So I get how to find the moles in the whole entire compound, but I don't get how you're finding just Ni2+.
So, okay, so maybe this isn't still fair. So we can take our nickel and our nickel sulfate, which we have 200 grams of. We can multiply that by 1 mole, has 263 grams. And that's going to give us moles nickel sulfate hexahydrate. 200 divided by 263 is going to be like 0.75-ish. I've got a calculator right here. Let's check. 200 divided by 263. 0.76. So that's how many moles of nickel sulfate we have. We can do the same thing with our nickel chloride. Now, why am I focusing on those and not the boric acid? There's no nickel in boric acid. So I'm going to go ahead and also take the 115 grams of nickel chloride we have, multiply by 1 mole, has 237 grams. And that is going to be like 0.5-ish. Let's see, 115 divided by 237, 0.485. Notice how many nickel atoms and how many nickel ions are in each nickel sulfate? 1. How many nickel ions are in each nickel chloride? 1. So that means if I add these two up, and we're going to learn more about stoichiometry in the future, but essentially I can take this and I can multiply by 1 mole nickel 2+ for 1 mole nickel sulfate. And I can do the same thing here. I can multiply by 1 mole. Do I see it? Nickel 2+ for 1 mole nickel chloride. Sorry, it's getting scrunched there. But the point is, that means numerically these things are just going to get added together. Plus 0.76. And I'm going to get 1.2, let's round it properly. Let's call it 1.25 moles nickel 2+. And notice, I haven't done anything out of the ordinary. I haven't done anything that's more than just a unit conversion. Though, I have done some unit conversions that we haven't really spent much time on in class, right? We haven't talked about these mole conversions yet. And that's, again, part of the reason why I'm like, this question wouldn't be fair on the quiz.
I just have a question just about moles in general. 1 mole is equal to like Avogadro's number. Right?
Yeah.
It's that many things.
Yeah.
Okay.
And for us, it's usually going to be atoms, ions, or molecules that we're counting.
Okay. So 1 mole, a certain amount of atoms would be that many, like no Avogadro.
Yeah, so I could multiply, like, so if I had half a mole, that's about
Oh.
half a mole, that would be like 3.01 times 10 to the 23rd
Okay.
ions.
Okay.
And it'd be half that, which is why you can have a fraction of a mole even though you can't have a fraction of an atom.
Yeah. Okay.
Because this represents trillions upon trillions of atoms. So this gets us our moles of nickel. So that's the moles of nickel that would be present in solution. How would the number of moles of nickel change if another 500 milliliters of water was added? If I add water, does the moles of nickel change? It doesn't. How would the concentration change?
Go down.
It would go down. That's a dilution. Right, and I want to point out something else. Notice, even if you couldn't solve part B, you could theoretically read part C and figure it out still. Right? One of the things that's really challenging for me is I write exam questions that have like A, B, C, D. People can't do part A and then they stop doing the question. It's like, no, there's still things you can figure out. There's still places where you can show me understanding. So in part C, you can tell pretty obviously adding water is not going to change your nickel concentration, but it's not going to change your moles of nickel atoms, but it is going to change the concentration because you're changing the volume.
Do we have to calculate what that concentration is?
I think that's part D. No, it doesn't ask you to calculate. It just asks conceptually, how would it change? Concentration would go down. All set?
Yeah. I actually have one question now.
Sure.
For number 17 on the other side, is that just M1V1 equals M2V2?
Yep.
It is?
Yep.
Okay. What would M1 in V1 be in that case? Just because I was kind of confused by it.
So these are all. M1 is going to be the given volume, the given concentration of stock solution.
Okay.
V1 is going to be the given volume of stock solution.
Okay.
V2 is going to be the total volume after the
40.
after the water's added.
Okay. Cool. Yes.
Total volume.
I was just tripping up on that.
If you just divide by 20 again, it looks like you're doing the same.
Yeah, that's why I was like, okay, cool.
Yeah, yeah.
All right. Thank you very much.
Yeah, you bet. See ya.
Yeah.
You what? Yeah. Did you do the M1?
I'll look at it.
So then part D and part E is where you need to calculate the concentration. So part D is asking if you have this number of moles, and notice it's in 1 liter. So the number of moles divided by 1 liter, this is also going to be your concentration is 1.25. Because at the top, again, back in the original problem, it says all in 1 liter of water. Right? Now you could say, well, 200 grams of nickel is going to have some volume off that, but let's say that the total solution is about 1 liter. That's going to be your concentration.
Okay, because I had just 2 variables. I had epsilon and concentration.
Right, so you can get the concentration from part B. And then in part E, it asks you to use the concentration from part C. So you're going to have to change your volume. You're going to have to do M1V1, M2V2 to get a new concentration.
Mm-hmm.
But I really think besides the unit conversion, I think I should include the molar masses in the problem. And I feel like the rest is pretty straightforward. And if we did this after Thursday, I think it would all be straightforward.
Okay.
But still make you think, hopefully.
Okay. So for 21, it says that the solution is diluted by a factor of 10, I think, for B. So that would change the concentration
Yeah, if it's
and
by
the absorption?
yes,
Okay.
by a factor of
10.
Yeah.
So both by a factor?
yeah.
So 21B.
21B.
He says
Oh,
that
sorry.
we're going to be using the concentration.
They're looking at the other one.
Oh,
Yeah,
okay.
we did that one earlier together.
Oh, okay.
So that's why they're
Like
probably
the
not
same.
paying
Okay.
attention to
So
this. So
will it be on
it's on the video and I'll
Okay.
post it. Yeah.
All right.
Did you have any other questions? So we did 21, 22, and 19 earlier.
I think I just have questions on 21 and 22. So
Okay.
Yeah.
Do either of you have?
No, I don't.
Okay, I'm gonna go ahead and stop this video. No one's watching anyway. Hopefully you'll all watch it later.